ever just stopped and wondered how you'd connect a bunch of different points in the most efficient way possible? It's a question that pops up everywhere, from building computer networks to designing entire cities. Well, today we're going to explore this really beautiful and elegant solution to that problem. It's called a minimum spanning tree. So let's start with a little thought experiment. Imagine you've got a group of islands, and you need to build bridges to connect all of them. Simple enough, right? But here's the catch. Every single bridge has a different cost to build. Your job is to make sure you can get from any island to any other island, but for the absolute lowest possible cost. Where would you even start? In the world of computer science, we actually have some neat terms for this stuff. Our islands, we'd call those vertices. And the bridges we could potentially build, those are edges. The whole thing, the entire network, we just call that a graph. Now, there are a ton of different ways you could build those bridges. Any set of connections that links every single island without making any closed-off loops, that's called a spanning tree. And that brings us to the really elegant answer to our island puzzle. It's called a minimum spanning tree, or MST for short. It's the one spanning tree where, if you add up the cost of all the bridges, that total cost is the absolute lowest it can be. It's not just any way to connect everything. It's the cheapest way. Okay, so we have this really cool idea of a minimum spanning tree. And, while it might sound like just a fun little puzzle, this concept is actually at work all around us, in systems that we rely on every single day. For instance, think about laying out water pipes for a brand new neighborhood. You've got to connect every house to the water main, but you want to use the least amount of pipe possible, right? Well, that's an MST problem. Or what about designing a phone network to connect a bunch of cities at the lowest cost? Same idea. It gets used for everything, from optimizing airline routes to making the internet itself run more efficiently. The minimum spanning tree is kind of like this hidden blueprint for efficiency in our modern world. So, how do we actually find this perfect, low-cost network? Well, there are a couple of ways. Let's start with our first method, which is called Kruskal's algorithm. This one, it takes a big picture approach. The logic here is so intuitive. It's what's known as a greedy approach, which basically means it just focuses on making the best possible choice right here, right now, without worrying too much about the future. The rule is incredibly simple. Look at all the possible bridges you could build across the whole map and just always pick the cheapest one. The only thing you have to look out for is creating a closed loop, because, well, that would just be a redundant connection. All right, so let's watch this in action. We start with all of our islands, or vertices, completely on their own. Totally unconnected. Kruskal's algorithm scans every single possible connection and finds the absolute cheapest one. In our example here, that's the bridge between island G and island H, which has a cost, or weight, of 1. So boom, we add it to our network. Our very first connection is made. Okay, now here's where it gets really interesting. The algorithm finds the next cheapest links, and it turns out there are 2 of them, both costing 2. So we add them both. And notice what's happening. We're not just building out from one single spot. Instead, we're creating these little separate clusters of connected islands, wherever the cheapest links happen to be. Now for a really, really important step. So after adding a few more of the cheapest edges, the next best option is the bridge between I and G. But wait, if we add that one, we'd create a closed loop. See, we can already get from I to G by going through the other islands we've connected. So adding this direct link would be totally redundant. The algorithm sees this, and it wisely skips it. And the algorithm just keeps on going like this, adding the next cheapest edge, as long as it doesn't create a loop, until every single island is part of one big connected network. And what we're left with is the perfect minimum spanning tree. It's pretty incredible, isn't it, that just by making the simplest, most obvious best choice at each and every moment, we end up with a perfectly optimal network for the entire system. Now let's look at another way to solve this very same problem. This one is called Prim's algorithm and has a completely different philosophy. Instead of looking at all the cheapest links across the entire map, it starts at just one point and grows the network outwards, almost like a crystal forming. The rule for Prim's algorithm is also beautifully simple. You pick any island to start with, it really doesn't matter which one. Then you just look at all the bridges connected to that one island, and you build the cheapest one. So now you have a little network of 2 islands. From there, the process repeats, but with a little twist. See, you don't just look at the last island you added, you look at all the possible connections coming off of your entire growing tree. And from all of those potential options, You again pick the single cheapest bridge that connects you to an island you haven't visited yet. You just keep repeating that process, always expanding your single, growing tree with the most economical next step until every single island is connected. So let's break it down. Here's the key difference. Crisco's algorithm is all about the edges. It takes this global, top-down view of every possible bridge and picks the cheapest ones first. Prim's algorithm, on the other hand, is all about the vertices. It's focused on growing one single connected network by always just adding the closest new neighbor. They're two totally different ways of thinking about the problem. And yet, here's the really fascinating part. Even with their completely different approaches, both of these simple, greedy algorithms end up finding the exact same perfect solution. For the network we've been looking at this whole time, the final cost of that minimum spanning tree is 37. It doesn't matter if you use Kruskal's big picture method or Prime's organic growth method. The minimum cost is always 37. You simply cannot connect all of these points for any cheaper. It is the provably most efficient solution. And that, I think, is the really beautiful idea at the heart of all this. It tells us that making a series of simple, locally optimal choices can actually lead you to a globally perfect solution. You don't always need some complex, grand master plan to find the most efficient path forward. There's something really comforting about that, don't you think? The idea that the best path forward, whether you're building a network or just navigating your way through life, is often the one you build just by making a series of simple, good choices, one after another. Thanks so much for joining me for this explainer.